Okay, so this video is going to go through transversable graphs, and it's just a bit of language. So a transversable graph has a trail that includes every edge in the graph. So pretty much you use every single edge in the graph, and we should know that for trails, repeated edges are not permitted, so you can't repeat an edge, and repeated vertices are permitted. So if you look at this graph here, go from A to B to C to A, you've repeated vertex A, that's okay, and you go back to C, you repeated vertex C, that's okay. But we haven't repeated any edges, 1, 2, 3, 4. So that's a transversable graph. There's a couple rules that we can use. So number one is a graph will be transversable if all vertices have an even degree. So if you look at this one here, you've got it's degree 2, that's 1, 2, that's degree 3, that's degree 3. So this one is not all vertices are even, but it has exactly 2 vertices of which are odd. The odd numbers are, 1, 3, 5, 7, etc. So if it's transversable, then you're either going to have a circuit, a cycle, or a trail for your paths. Okay. So if we look at this example, number A, we look at it and every vertex has degree 2. So the number of connections to each thing is 2. So all vertices are even, therefore it is transversable. And then if you went from A to B to C to C to D, D to A, that's classified as a cycle because it goes back to the same vertex. So that's that one. And then example B has 2 vertices of degree 3, so 2 odd vertices, and the rest are even, so it's going to be transversable. So it's transversable based on that. And the way that you get a trail which goes through every edge with these ones is you start at one of the odd vertices. Okay, so just start at one of the odd vertices and go through until you hit every edge. So G to F to E to H to I to G covers every edge. So we're just sort of doing it by inspection at the moment. Okay, so that's transversable graphs. And then we have these things called eulerian trails and circuits as well. So basically you need a connected graph, and a eulerian trail is a trail that includes every edge, and a eulerian circuit is a circuit that includes every edge as well, but goes back to the same original vertex. So you're going to get a eulerian trail if all the vertices have even degree, or you have 0 odd vertices. And you're going to get a eulerian trail if you have 2 odd vertices and the rest are even. Okay? So there's a process to follow when you're doing it. So if they're all even vertices, you can start at any edge, or vertex rather, and if there are 2 odd vertices, you start at one of those vertices and then try and find a path which goes through every edge. So if we look at example A, this can be classified as a eulerian circuit, and we go, it's all even degree. All even degree says eulerian circuit. Alright, and you have to go through every edge, and you start and finish at the same vertex. With circuits, you can pass through the same vertex. With circuits, you can pass through the same vertex more than once. So all even, it's going to be a eulerian circuit. And then you can just state what they are. So if you go from A to B to C to D to A, that's the eulerian circuit. Alright, and this one here, you've got a graph with two odd vertices, so you start at one of the odd vertices and you just follow it along until you until you cover every edge without repeating edges. So there is a process which I'll go through in a moment, but we can just see that if you start at 3 here, and if you go up here, down here, back up here, back through there, and back through there, you go through every edge. Okay, and you're going to start at an odd vertex and end at an odd vertex for a eulerian trail. Okay. Now there is a process which you can follow for more complex ones, and the idea is you don't burn your bridges. So remember, a bridge is an edge which, if you delete it, it's going to make the graph disconnected. So if I deleted this graph here, you would get something that looks like this, and that's definitely a disconnected graph. Okay, so here's the example. I'm currently borrowing this from a university professor from the internet, so I thought I'd mention that. You can just Google Euler circuits PDF and it'll come up. So basically we start in an odd vertex to find a Euler circuit or trail. Okay. Now, what we do is we start at one of these and then we delete an edge such that the rest of the graph stays connected. Okay, so if you start at F here, if you delete E, then the blue is still connected. Alright, and you follow it along. So once you've deleted E, you have to delete A, there's no other choice. Okay, and the blue bit is still connected. Keep going. You have a choice here. You could have gone from A to B. You could have done that because then it would still be a connected graph, but they've decided to delete C. Okay, so if you delete C, that's okay. The blue bit's still connected. Okay, now if they're choosing any edge such that you're not burning a bridge, pretty much. Okay, so they choose to go through here, which is okay. The rest of the blue bit is still connected. And then once we have that, what happens is we have choices. And if I deleted, A, B here, then I would have a disconnected graph. You'd have this isolated vertex and you'd have the rest of the blue bits here. So it would become disconnected, so you can't choose that one. So they've chosen to go down here. All right. Now, again, you choose another edge such that you don't cross or burn a bridge. So if you were to cross here, you would have a disconnected graph because you would have this happening if you deleted the D to B. So that would be disconnected, so you can't do that. So you choose to go this way, it's still a connected graph, the blue bits. And now you have to go to C here. and you continue through, and eventually you get your eulerian trail, because we started at F and finished at A. Okay, so it's a circuit if it starts and finishes at the same place. All right, so we get a eulerian trail there. Okay. So there is a method for eulerian trails, but you can often just do it by inspection, by trial and error. Unfortunately, with Hamiltonian paths and cycles, you have to do it by trial and error. So basically, we have this definition that a Hamiltonian path passes through every vertex in a connected graph. It may or may not involve all of the edges. Okay, so it has to go through every vertex. So this purple one here is a Hamiltonian path. It goes through every vertex in the graph. Now, a Hamiltonian cycle is a Hamiltonian path, but it starts and finishes at the same place, the same vertex. So the green one here, you start at A, you go to C, you go to B, you go to C, you go to E, go to D, go to B, go to A. Alright, so you start and finish at the same vertex and goes through every vertex. So that's a Hamiltonian cycle. So there's no rules for finding those ones, you just do it by inspection and trial and error. Okay, so here's a little summary. Right, so trails, eulerian stuff is pretty much to do with going through every edge, whereas Hamiltonian paths and stuff is to go with every vertex. We have the summary that a eulerian trail is going to happen if you have two vertices with odd degree, and eulerian circuit is going to happen if you have all even degree vertices. All right, and the circuits start and end at the same vertex, whereas the trails don't. All right. So that's the summary. All right, on to what is a tree. So a tree is pretty much a connected graph, all right, where you don't have any loops, you don't have any multiple edges, and you don't have cycles. Okay, so this one is a tree, it's a connected graph, there's no loops, no multiple edges, no cycles. This one would also be a tree. This one is not going to be a tree, okay, because there's a cycle here. And this one is not going to be a tree because there's multiple edges. So here's another graph. They all have single edges, right? A multiple edges, we have go from a vertex to vertex, and you have more than one links, so they're multiple edges. So we should be able to identify trees or not trees, and then we have some properties of trees. So if you have n vertices, you always have n minus 1 edges for trees. So for example, here's the simplest sort of tree you can have almost. 3 vertices, 2 edges. Keep going. 1, 2, 3, 4. 4 vertices, 3 edges. So if you complete the pattern, right, if you have n vertices, it means you have 1 less edge. All right, a spanning tree is a tree that connects all the vertices of a graph. And a minimum spanning tree is to do with like weighted graphs. So you're going to see that in a little bit. I'll quickly illustrate, you know, if you have this graph, all right, if this is your graph, you could have a subgraph, which is a smaller part of the big graph. Okay, so this is the total graph. So this would be a subgraph, and it's also a tree, B, A, C, D. This is a subgraph. It's a smaller part of the bigger graph, all right? But this is not a spanning tree. It's not a spanning tree because it does not go to all the vertices. So it's a subgraph, it's a tree, but it's not a spanning tree. So if you then, sorry, my pen is being a bit funny. If I do this though, A, B, C, D, E, this is a spanning tree. It's going to every single vertex of this graph. All right. Okay. I'm not going to do that. I'm going to do Prim's algorithm. So Prim's algorithm is about finding a minimum spanning tree, and it's pretty easy. You just connect. Well, first of all, you pick the smallest edge, and then you just pick the smallest connecting edge every single time. So here's a graph, right? What's the smallest weight of one of the edges? So you have a 2 here and you have a 2 here. So you can start at either of those. So if I highlight that, I've decided to start there. And then I just pick the smallest connecting edge, the smallest weight. I'll say that again. I pick the edge with the smallest number or the smallest weight associated with it that connects this stuff. Okay, so I can go to beta 8 is 8, beta D is 6, A to D is 5, A to F is 6. So the smallest one out of those is the 5. And then I look at all the stuff that I have and just pick the smallest edge, which is connecting what I have. So, you know, I can go, and you don't go back, you don't create cycles. Okay, so I can go from B to C as 8, or I can go from D to C as 3, or I can go from A to F as 6, so the smallest is 3. And then from that, I pick the smallest possible thing without creating any cycles or anything. So I can pick the 7, or I can pick the 6, or I can pick the 6, or I can pick the 5. So the 5 is the smallest, so that one. And then finally, smallest is 2. And have I got to every single vertex? A, B, C, D, E, F, I have. So that's the minimum spanning tree because it's the smallest total weight of the tree, of a spanning tree of that graph. So the application of this is in some connector problems, all right? So here's an example. At a showgrounds, 11 locations require access to water. These locations are represented by vertices. The dashed lines on the network represent possible water pipe connections. And the number on the dashed line shows the minimum length of pipe in meters required to connect these. All right, so basically, you know, from here to here, you have some location, and there's 60 meters of pipe in order to connect these guys. So you want to connect them all with water in the smallest possible way, because that's going to be the smallest possible cost, okay, in general. So we always start by picking the smallest possible edge. So let's pick the smallest possible edge. You've got 40, 50, 60, 70. So it looks like 40 is the smallest. So let's just pick this one. Could be any of them, right? So that's that one. And now I pick the smallest connecting edge from, you know, the vertices that I have, So 60, 70, or 50, 60, 50. I can go here, I can go here, doesn't matter. So let's go this way. All right, then from what I have, what's the smallest connecting edge? Well, 40, 60, 70, 60, 50, 60, smallest edge is the 40. Okay, and then from that I say what's the smallest connecting thing that I have? I can go to 50 or 60 or 50 or 60 or 70 or 60 or... So it's going to be the 50, so let's just do this one. It doesn't matter which one you pick. And then I pick the smallest connecting thing that I have. So I have a 50, 60, 70, 60, so the 50 again, this one. Again, I pick the smallest connecting edge, and I don't want to create any cycles or anything, so I'm not going to go back to 70. I'm not going to connect these things because I've already connected up the water pipes to the different locations. I'm not going to go backwards and connect again. So it looks like from here, go 60, 70, 60, 70. So it looks like 60 is the smallest, so pick one of those. And again, you look at the smallest connecting thing. So you have 70, 70, 60, 70, so the smallest is going to be 60. And the smallest connecting thing from there is going to be the 40. And then the smallest connecting thing is going to be the 60 and the 60. All right. To calculate the total length required, you just add up all the numbers. Okay, so that's that one. I'm just going to check my answer. Okay, so that was pretty much a VCAR exam question. Yeah, it looks like I got it right. Okay, so that'll be it for that video.